which is the domain called ontology. So ontology essentially is the study about what does fundamentally exist and how do we derive other things then based from what we originally postulated. So one starting point is that you could say, well, there is some indivisible thing like an atom, and then from there you try to build up your worldview. That has held for some time, but there were some limitations on the way down that suddenly it was discovered that an atom is not just a singular thing, but it has structure, substructure. And more we also begin to learn that it's not just the structure that matters, but also its history, right? That two things that could be, based on their properties, described as equivalent, suddenly in certain topological configurations, for example, it matters which path a particular object took. Even though that they may look the same in the beginning and in the end, it still matters which path they went. So that's on the way down. And on the way up, we have the increasingly higher and higher levels of complexity, complex structure, which is also leading to challenges of how do you have a kind of a dumb, simple material thing, and how can that suddenly become dynamical and rich and complex in its structure, in its, well, behaviors or paths of unfoldment. Much like ultimately we have human cognition, we have subjective qualitative experiences, we have judgment, we have conscience, and intuition and things like that. And it's very hard to explain these things coming from the ground up. So what I want to start first, I don't want to go too much into the technical discussion, even though it's a very, very interesting one. That would just take us back to Bell with his beables, and then structure from ontology to build up a directed structure. And this is one of the statements that Tim Modlin makes. He says, like, well, people are saying, oh, general relativity has turned time just in another dimension of space. But he points out that's simply because we're using mathematics. We're just pulling something off the shelf that is a four-dimensional structure, and we use 3 for space and 1 for time. But the mathematical structure that we're using for that is not a directed one, even though in everyday human experience we always perceive a direction, or at least an order in one singular direction in time, mainly in the past. Or, I mean, past, future, just one simple direction. And he says that's completely unjustified to use these sort of structures. And then there's another problem, that we have this habit of having a scale, a notion of scale, a measurement, a measuring rod baked in on the very basis of whatever structures we then use. And that also might be unjustified starting point where we should focus on more general criteria, such as proportions and relationships and relative motions, relative scale, relative positions before any scale. And then on top of that, we can then take a structure and map it into a particular, it's called a measurable space, a measure space. So a space which is measurable, and then on top of a space which is measurable, because not all spaces are measurable, then you impose or project a measure. And then you can say, you take meters or feet or whatever measure you impose. Obviously, the space is the same one, the physical world in this case, whether you use meters or inches, right? It's just a different measuring scale, which is imposed or projected on top of. And so where I want to start out is on a much more basic level than anything to do with scale and all the technical structures that grow on top, but go back to the very well, fundamental choices or selections, or if we want to consider any of these starting points, as long as it is a valid one, it's not necessary that there's only one singular starting point to analyze and reason and explore reality. But they certainly all should lead to consistent interpretations, understandings, models, and results to the extent that we share a common reality, right? If I have a subjective dream, or if I imagine something in my mind, there I can imagine all sorts of things that are different from the external world, but the world that I perceive from the outside in, there, or we would distinguish imagination from perception as to what others also can perceive. So if many people around me share an overlapping experience, it doesn't mean that the experience is identical, but that we can point to a tree and we know the same object being referred to, the same pattern, the same structure. It's on that level where we want to find the generalities of experiences and perception. And if we really start peeling back layer upon layer, you end up with the question of cosmogenesis. So cosmogenesis is the genesis, like the generation, the origin, if you will, of cosmology, like the large structure of the universe within which we find ourselves in. And then the cosmology is, in a sense, kind of a projection, a model of what kind of reference points we take as a particular scale, as a particular event, and then we project it out into the universe and also into the history, and then that's our story, how we got to be here. A separate question that rides on top of that cosmological assumption deals with teleology. So a telos is a structure with, like a telescope. It can be compressed, and then it expands in that linear direction that a telescope does. But a telos can be more rich, more varied than simply two or more poles stuck inside each other that can only expand in one direction. So telos and teleology is a much more general inquiry as to, is there any discernible pattern or principle or regularity by which the whole thing unfolds? There we have this kind of mechanistic understanding of the universe, which holds for many things. It breaks down when we go into divergent spaces, because these Euclidean Cartesian models, like the Newtonian understanding of the world that treats the world as a billiard table, they always try to explain what comes next based on what has come before. And therefore they imply that there's a certain kind of predetermination. And if you could know the whole universe sufficiently close, then you could predict the whole outcome. And that's appealing to many people. I would say many people that are predisposed to a kind of a reductionist, materialistic understanding of the world, because it's very compatible with that one. But it ultimately breaks down when you really start to either go into very complex system or in very high energy interactions or very low level interactions. In all these cases, you end up finding results or discovering outcomes of experiments, of tests that you do, which are inconsistent with what that Newtonian mechanical reality would, what you would predict based on those. So it holds as an approximation for kind of like human level interactions, but it doesn't really hold to understand the reality at large or at the very small. And so one thing that we can always observe when we involve the mind is the act of differentiation, that we select one thing and differentiate it from the other. So for example, if you now look at your screen, you can see me, and then you can see the background, like the surroundings, and you can more or less clearly distinguish which part is me and which part is, or that rock over there, or well, the other way, or a door, or whatever object you identify. you can refer to it, and you do this in an act of differentiation. You associate a concept or an identity with one particular thing as distinct from everything else. And we often end up with an intuition or a sensation where we perceive things to be atomized, to be different, to be separate from each other. And that is largely because we cannot see the trace. The trace is like the trail, if you, in a sense, the history. And if you would always see the history of every object, then you would see, for example, let's keep pointing in the wrong direction. You would see all the history that has been written on that whiteboard. Or if you have, if you would see the history of my mind, then you would see the history of everything I ever thought and I've ever experienced. And that could be very confusing to figure out what the situation is right here, right now, if I'm simultaneously also experiencing all sorts of other situations that I've experienced at some point. And therefore, we have this selection mechanism. It's not that we throw away the memory, but we kind of put it into a certain archive where we can access it, and we distinguish it from the current moments that we are in this moment aware of and perceiving. And that step, which is just essentially an artifact, in a sense, a side effect of cognition, for pragmatic reasons, it's necessary to focus on what you're dealing with right now and not consider all sorts of other things, because otherwise you would end up with too many contradictory, let's say, once I've been too hot and once I'm too cold, and now I'm experiencing both at the same time, then I end up in a confused state about what my situation is and what I should do. No, I need, whatever the past was, I can leave behind in memory, in archive, accessible. If I need to look something up, what happened then, what was the outcome, would an alternative course of action have been preferable, right? As a debugging, as a learning system, and as a coordination mechanism, memory is very useful. But we need to make this selection of zooming in what is right here, right now. And this leads to an apparent duality, to an apparent separation, where we distinguish one from the other, usually a domain or an object, a subject, from the rest. And when we now look at how we arise, like how you as a human came to be, but also maybe how our species came to be, or how organic life came to be, or how material structures came to be. Everything, in a sense, if you look backwards, it always looks like it has to come from some previous cause. But that is based on the assumption that our universe works with like a billiard table, where one ball is moving because it has been knocked by another ball and has been knocked by another ball and has been knocked, eventually, usually going back to a human. But then on the level of the human, where you have free choice, where you can choose in which angle and which position and which speed, to the extent that you can control it, right? You can choose the impulse that you want to introduce into the system, and then from there you have the billiard system, which is approximately Newtonian. But none of that is causation. Just this impulse propagation is literally just that. It's like one billiard ball transfers momentum onto another, knocks the other one, goes on, goes on, goes on. And as a path to explain anything, to come up with a story, if we're only looking for causation to have happened in the past, then we will always just, whatever we end up discovering, then is that, well, how did that happen? And then how did that happen? And how did that happen? And we keep going back and back and back, further and further, until today our best theories basically say, like, well, in the beginning, everything was so jammed up together and so energetic while we have this expansion, which the expansion itself, so when it comes to cosmology, when people talk about inflation, it's not the same inflation like if we have currency inflation, and it's a sense of a dilution. But what is assumed there is that you had an exponential expansion, that in the beginning of space, that expansion was so extremely rapid that basically space was being ripped apart, and fluctuations were in the middle of being random, or again, that's the story. How valid and how useful that perspective is, we'll get to see. But that's what is assumed today, that while we had these quantum fluctuations, they kind of got expanded and ripped apart. And then that led to imbalances, and then these imbalances led to the imbalanced distribution of matter throughout the universe, and then through gravitational attraction, you had galaxies form, gases, like clouds of gases collapse into stars, forming solar system and so on. Okay. Now, Nima Arkani-Hamed from Princeton, he points out that the question is not why the universe is expanding. We had mathematics that could that actually make this expansion very, very natural, except if you calculate it, and it's basically just a ratio of Planck unit and Planck distance and Planck time. You end up with a vacuum density, with a vacuum energy, and when you calculate how fast that energy would be expanding, it would be doubling in size. That's how expansion is measured, because it compounds, right? You need to have essentially a recursive definition that you can keep running. Like every interval, it keeps doubling and doubling and doubling, because whatever the space that you expand, then that new space, that expanded, inflated space, also keeps expanding, and so on. So according to these models, I think the expansion would double pretty much every Planck second. Planck second is like 10 to the minus 43 or something ridiculous. 10 to the minus 34 maybe. It's a very, very small number. So it means like per second the universe would expand a gazillion times, being a very technical number here. No, just a ridiculous expansion where everything would fly apart and expand at a rate where no structure could ever form. Like not just no planets but no stars, no galaxies. Like everything would basically just empty. And somehow this is miraculously balanced with a counteracting force where the gravitational mass somehow seems to almost cancel out the expansion, where you have areas with very little matter, it seems that the space is expanding, and where you have concentrated matter, like let's say a solar system or even a galaxy, if you look at a large picture, a galaxy, even though it's mostly empty, it still has it's a high concentration of mass with regards to the intergalactic void around it. And then you can zoom in, you can say the same on a solar system, it's concentrated, but it's still mostly empty because it's just a star and a few planets. And then you go to the planets, you go all the way down to the atoms, and the atom still is actually mostly empty with some very small core, which we then can kind of probe with experiments and interactions. Okay. So we often hear that our best scientific theories are counterintuitive, and that just means that we have to realize that our intuition has evolved and has developed in a context of human level interaction. That means moving at speed and size, roughly the size of humans. It's like with water waves, you can kind of interact. Sound waves you can hear. With light waves, it becomes much more difficult to control them, but they're still on a level where we can interact with them, but only actually a very narrow spectrum is that we can see. A water wave, you can see it at any size, right? Even if it's a small ripple, if you look closely, you can still see the wave. And if it's a huge mountain of water, you can still see it. With light waves, it's not like that. It's like you have a narrow spectrum that you can see, and to most of it, we're oblivious. And so the further we go away from these, what I call human level interactions, like meter, kilograms, that kind of stuff that we, I don't know, kilometers or miles per hour, there our intuition is kind of like a heuristic. Like it's an experience, an experienced value that you just kind of take from, I don't know, when you walk across the room, you can roughly gauge how far you are and how far you're not going to randomly accidentally run into the wall because you were one order of magnitude off in the speed you wanted to move, because on that level the intuition works really well. When it comes to scientific theory, this intuition often stands in our way, and as a result, we often do not have sufficient confidence in the theories, in the prediction of our own theories. And then when we don't like the prediction because of some essentially mental resistance, we end up looking for alternatives, looking for different models, different explanations, so that our predictions agree with what we would say is intuitive. I think this is often being done prematurely, that we kind of jump the gun and go into trying to fix our theories before we really examined what would the implications be if the math would actually be true. So I just mentioned one, that basically the universe would double every 10 to the whatever, 10 to the 30 or 40 seconds, 10 to the minus 40. So like a 1 with 40 zeros per second. That's how many times the size of the whole universe would double, according to this one prediction. One way to look at this is like, well, I'm looking outside, and obviously that's not what's happening. Another way could be to say, well, if that would be true, that means the universe that we're looking at right now is only 10 to the minus 40. I should look up the number to be exact, but right, you get the ballpark idea. Right? 10 to the many iterations. So the current frame, the current moment of the universe is actually very, very, very young. That means it only in the tiniest fraction of a second, it was just born out of however a universe is born. And then all the structure and all the galaxies and universe and everything had to form in a way which then leads to the configurations and the experience where we're at today. Now, if we're thinking in terms of speed of light and chemical reactions and physical stuff buzzing around, you can say, well, there's no way to get to within that short amount of time to get to the complexity that we have today. But that's assuming that the universe grows within time. But we want to go one level deeper. And if we want to see how time itself arises, then you have an additional degrees of navigational freedom. You know, like imagine you're like in an elevator and you can move around in 3 dimensions, but then the whole elevator or the whole box that you can find yourself in can move up and down, and maybe you can even load it onto a truck and drive it around, or put it on a plane and fly somewhere. And inside you still have the same reference system, the same box, and it seems locally completely consistent. While you're not changing the box, you take a step back by that is increasing at least 1 dimension of freedom, and then suddenly you can take the other space and move it around. And if you think of a piece of paper, you can take a line, and then the line is just 1 dimension, but then because you have a piece of paper, you can translate it and move the line around or rotate the line itself. And on the line, if you have points and they're distributed in a particular way, as long as you don't stretch the line, the proportions are exactly the same. So the line doesn't actually care which way it's oriented, because it's oblivious to this higher degree of freedom, this higher dimensional space in which then the line is embedded. And so in a similar way, the universe which we observe is embedded in a higher dimensional space, and that's where this point of Nima Arkani Hamed becomes really kind of confrontational with your own concepts, when people explore the question of what is before the beginning of time, where he points out that it's not that we don't know what's before, it's that how we got to the beginning of time, we can't extrapolate it further, because our notion of before, the beforeness, or the very idea of sequential order, you can't ask what was before the beginning, because the beginning is by definition is before anything else. So how you got to the beginning cannot have happened within time, because time did not exist before that. So you need ontological, you need to start with another structure that then gives you on a higher level the structure that we experience as time. And when you study these things in the domain of philosophy, then, or in certain spiritual traditions, they make use of the same cognitive structures to explore these sort of origins, origin of yourself, origin of reality, or origin of the universe. And you go not just analytically, that you kind of intellectualize and theorize about what it could mean, but that you go in an experiential, ultimately a visceral sense. You go and get a first-hand experience of what a particular perspective must have been like, felt like. And then you realize that before whatever happens, whatever exists, before that existed, before I existed as a human with a biography and everything, before that, there was a certain, it gets tricky to use the right word. Sometimes you hear about non-existence, but then out of non-existence, how can non-existence exist in a sense? Because it is what doesn't exist. And then how do you get existence from non-existence? So that you have a kind of a duality there, which within this duality from non-existence and existence, you can't say that, you can't give as an argument, or I think that's not a defendable position to say, well, everything exists because it didn't exist before, because that means also anything else could have existed, right? By that kind of reasoning. So how do we get from not existing to existing? Well, the first confrontation that we have to kind of meet is that there is something before manifested existence, before time, before space, before all the structure and knowledge in the universe. In a sense, before the universe was born, if you will. And that is called the ontological shock of non-being. Like when you get there as a visceral experience, it's really like it can be quite an intense experience, because it can feel like awakening. It can feel like a electric jolt. Sometimes we're confronted with fear when we're not familiar what we're headed into, because we are so used and so attached to exist and to have a body and to be able to touch and interact with things. When all that is stripped away, and yet our experience remains, it can be quite startling at first. But if you keep going back, and if you keep exploring and studying and discovering that condition further, then you see out of non-existence there is an if you hold both perspectives simultaneously, of that something can exist like the world, and it can come out of something that doesn't exist, like existence and absence, that which exists, that which is, and that which isn't. Like if you combine the two together, you end up with a third, something that lies beyond both. You have to be willing to conceptually go beyond duality. We're very used to this good and bad, right or wrong thinking, because that's where our intellect and our human mind functions. That's how we communicate. That's how we relate to the world. It's always one thing and another thing. I found this quite interesting. In the Chinese language, apparently everything is described in processes. So you have, for example, a process bird watching, which implies that there is a watcher and there is a bird being watched, and you cannot separate the two. You cannot have a watcher that isn't watching something, and you cannot have a thing being watched without there being a watcher. So there you have an almost natural way to always go on from a concrete level of object-subject and the relation. You go onto the meta level where you see how the two things arise. And this is the direction that I would like to take us now to go explore. I'll switch. Let's see if this works. All right. Oh, we have some shade here. Well. Okay, this I'm going to start with the understanding of Advaita Vedanta. This is how it was once introduced to me from Göttel, the author of The Big U, Paul Göttel. He said Vedanta works something like this. Like existence without there being any duality, like Advaita Vedanta claims to be Anta means the end, and Vedanta means the end of the Vedas. And Advaita Vedanta, Advaita stands for non-dual. So the non-dual perspective, the non-dual understanding of the of the conclusion, if you will, or the end of the Vedas. And it starts something like this. Existence just is, without characteristics, without differentiation. And it is all there is, and all, like all the potential of whatever could be, without anything being concrete. For the moment, let's shelve that for a moment, and we'll return to this Advaita Vedanta. I want to first introduce another concept, simply the concept of expansion. And if you think of expansion in the sense of creation, something that somehow is spoken into existence, if you go with that first there was the word, or first there was a will, or first there was an intention, or there was some primordial impulse that in its nature is creative, in its nature is kind of mandates or implies existence. So we had the ontological shock of non-being, but if you keep confronting and exploring that, then you suddenly end up with a certain, an irrefutable sense of this non-dual sense of existence being total. So sometimes we have the concept of like a neutral, well, we have a positive and a negative mind. The positive mind is where you go after options, after chances, after potential, and the negative mind is like your debugging mechanism where you scan for problems, for risks, for danger. And the negative mind is the part that keeps you alive, and then while you survive, the negative part keeps you safe from all the dangers of, like, I don't know, running into walls and off the cliffs and things like that. Then you have the positive mind, which allows you to realize potential and pursue certain creative endeavors or whatever you want to do while being alive. And if the two are balanced, you end up with the neutral mind, and the neutral mind is total. That means it's no longer dual, and therefore you no longer have this existence and absence of existence. But now you're dealing with an aspect of reality which cannot not be. It's irrefutable. And again, this is an experience that you can go on a visceral level. You can go so deep under the surface layers of your mind that it's not just the cognition and differentiation and identification with objects falls away, but eventually that you go beyond duality altogether, and then there is this sense of total irrefutable affirmation, in a sense of that which cannot not be. And that which cannot not be is, in a sense, it's neutral, it's perfect, but it's also already reflexively aware of itself. Again, this I'm not going to go open up a debate about theory, because people can speculate about all sorts of things. Everyone that will do the work and apply themselves to go and look for themselves has come to the same conclusion, and that is that even if you go beyond the mind, you do not cease to be. Your perceptions, your differentiations, your distinctions end, but your awareness of yourself and the subjectivity and the experience of this individuality remains and prevails. And out of that reflexive self-awareness, there is this potential, or this possibility of a thought. And let's start with that single first most powerful thought. So if we start out with just being aware, then that reflexive self-awareness kind of implies, without there being any structure, without there being anything else, it kind of is natural. Almost if you would think of, if you would find yourself blindfolded in a room, it would be natural to ask the question, well, is there something other? Like, is there a wall? Is there a limit to where I can be, where I can go? Or is there something else? Like, is there something to interact? Is there something in the room? Is there somebody else in the room? And so there's like a natural expansion of the awareness, which is led by the curiosity. Could there be anything else other than, we would say, me? But in this case, me is literally all that exists, because nothing else exists yet, right? We boot this up from the only thing that exists is the ability to exist and being aware of that ability. And out of that is generated a sense of expansion. We can take this as a expansion of awareness, but if we want to have a little bit more rigorous understanding, we can always look at where a similar principle is operative in nature and then draw it from there. So if I would take the first moment of expanding at the speed of light, a signal, like a radio wave or a light wave. Within the first moment here being the duration of a Planck second, so the shortest measurable time. In Eastern tradition, you have the notion of kshana being an instant of time and krama being a sequence. So a sequence always relates to instance. So from the first instance to the second instance, due to the limitation of expansion, like in this case with photons with the speed of light, you have a small radius which you start at a point, you're already aware that that point exists, and then implicitly you wonder if there's something else which could exist. And this gives you a kind of I'm drawing a little circle here to indicate that you expand it a little bit within 1 Planck second. And then in the next moment, if you keep going, you can keep expanding, right? And then you have like this radial expansion. And then in the next moment, in the third moment, this is just saying like I expand everywhere I can simultaneously, but due to the limitations of how fast I can expand, I can only go from moment to moment. And between two moments, since there is only a relationship that relates the two, they're always able to contract. So the actual distance, the duration, is not relevant. It's just that from one moment to the next, these are the steps by which, if you want to expand, you can say you expand through the whole universe at once. Okay, and then what? If that was done in one step, then what are you going to do in the next step? Then the expansion would go further, either exploring substructure within the universe, which doesn't exist yet in this case, or you just keep expanding into the environment, into your surroundings. Now, if we start out with all there is, and we're trying to expand into something else, that is already a little bit imprecise in the words that I'm using, because there is nothing else. So the only place where we can expand into is in something imaginary. So when I say each of these paths is contractible, that from one moment to the next, there is nothing in between, in a sense that you could accelerate this process infinitely fast, and the starting point and the end point will become one and the same. And this contraction is exactly what we observe in the case of photons. When hydrogen fuses in the sun, there's different numbers, but it's in the 100,000s of years range, sometimes more, how long on average a photon bounces around inside the sun until it finds itself to the surface, to the photosphere. And the photosphere is kind of like roughly the clouds of the sun, where then the light is shot out into the universe. And then from there, it travels another 8.5 minutes towards Earth, in case we get a chance to see it. And then it gets reflected maybe a few times, maybe bounces off a few atoms in the atmosphere, kind of deflected a little bit, shifted in color a little bit, and then maybe it hits either a wall and gets reflected on the wall and hits our eyeball, and then we see the wall illuminated by the sun, or we see the reflection of the sun in a mirror or sunglasses or all that. And that whole path that I just described, that from our perspective, from our frame of reference, takes several hundred years, mainly because the photon is bouncing along back and forth around the different atoms in the sun. All of that, from the perspective of the photon, happens at the speed of light, which means, well, now, so I didn't want to go into too many technical things, but I can't seem to help myself. if you want to go, whenever you go and approach the speed of light, like now talking in terms of a material body, the faster you go, the more you experience Lorentz contraction. And if you reach the speed of light, which is not possible for material like bodies with a rest mass like ourselves, but it is possible for, it's actually mandatory for all the particles which do not have a rest mass, such as the photon, then you have the Lorentz contraction is complete. That means what is perceived from our outside view, from our frame of reference, what is perceived to be a duration across space and in time, from the perspective of a photon, happens simultaneously. So this is a little bit tricky to wrap our head around, but Lorentz contractions essentially couples the emission point with the absorption point in the case of a photon. They are synchronized. They are actually identified with each other, and so you have two different points, local points in space-time, not in the same moment in time, but from the perspective of the photon's frame of reference, they happen simultaneously. Okay, so this is the sort of expansion that we always have, an expansion which is contractible, and then from there we can take that as the next ground for the next step, and then and so we can go outwards. But now, what happens if we look at this in a sense of a sequential order? So we have the initial moment here, and then we expand. I'm now drawing it from the side. We expand a little bubble, a little sphere. And then in the next moment, we expand a little bit further, going sequentially now from here to here. But on top of where that initial bubble already was, so this initial bubble, in the next moment, while we can go out further, the space which is already covered, now you have two bubbles. Like in a sense, you have now two bubbles on top of each other. One being the previous bubble, and then that being the sequential bubble. And then if you go to the third expansion, you have a third bubble on top. Oops, that's not very nice. And so on. So you see now here we have a direction of sequentiality, sequential order of individual events. I think my microphone just dropped. Check. Fix this. Let's see. Okay, check. Good. So, keeping this in mind, that this expansion that we're observing here is always, each step in sequence is an imaginary step, meaning it's a step where we, in our mind or in the mind of the universe, we have the idea of, could there be anything else, or a curiosity, is there anything beyond us? Which means either there has to be a limit to ourselves, that eventually we hit a wall, like that there is some limit and then we can't experience further. Then the question is, well, if existence was all there was, what is the wall made out of? If it's not from this unitary, primordial, non-dual existence, that means now we're already in a dualistic notion. That would imply that there is a separate thing. And then we can investigate that, and then we have to find a way to explain how both of those came about. Or, in absence of that, since it is an imaginary process, we can just keep going and just imagine more and more and more and more and more. And then that's one way to assume as a perspective to study and explore the history or the origin of our spatial universe, having now space like this and time like this. There's also a very interesting presentation by Sean Hartnell. I think it's called Webinar 96 or so. It's from the beginning of this year, about March, where it's more of an aside. It's not the main thing that he discusses, but he goes into matrix mechanics, and he shows how if you take a state at equilibrium, like Dirac first postulated this as the Dirac sea, that the Dirac sea is like a horizon from where you can excite one charge, like an electric charge one way, and then you create a displacement. Okay, maybe I should wave like this that you can actually see my hands. So if you have a horizon which is flat and you have the smallest level excitation, meaning like you excite a particle pushing it up, and then it's relative to the other horizon, the other horizon is lower, then that differentiation starts to propagate and move over time in a dimension, and that dimension has not existed. So in the mathematical infrastructure that he uses there, he doesn't start with time and space. He just starts with time and plots a function that generates an excitation, and then that excitation propagates. And so there, from the propagation in time, that would be, in our cases, would be this one, like having sequences of events, then implicitly the expansion would sequentially expand outwards. Okay, so that's the kind of the side bracket which I kind of wanted to open up conceptually, and now we're ready to go back to Paul Goethel's explanation of or introduction into Advaita Vedanta. And yeah, when he shared this with me, he said, look, basically start like this. There is nothing, and into that nothing you project, you just imagine a circle. You don't claim it's real. It's just made up. It doesn't actually need to have a scale or anything else. You just measure something that is, you imagine something which is closed. I would say that it returns back to itself is probably the key feature of this idea. If you would project it in 3 dimensions, also yeah, in the previous discussion, right, the circles, obviously the 2 dimensions were spatial, and then the third on top, I just made it up that one was temporal. In our physical world, we already have 3 spatial dimensions, so that the temporal dimension is an additional one that we do not directly observe. So sometimes it's easier to get rid of the spatial dimensions and replace it with time, so we can reason about them at the same time. So in this case, this is without dealing with space, dealing with space-time relationships, just a conceptual space like a canvas, and within that canvas we project a scope. And with that scope, we differentiate the focus, the inside, from everything else. So a circle in 2 dimensions delineates the area of the circle, and in 3 dimensions it will be a sphere, like a beach ball, you know, like a plastic ball, which is defining a volume. Like, so you can think of this as a sphere in 3 dimensions, or just as a circle with the area inside. And now you do this again. You project a second circle. You interproject them, you make sure that they intersect with each other. That's the only necessary condition. And by having 2 arbitrary regular things interproject, again, these can be circles or spheres, you will generate, at a minimum, these 2 intersection points. Now, if this would be in 3 dimensions, then you would actually, there would be, if you would see into the cross section, then you would have a circular area, not just the 2 points, right? Because if you have 2 spheres, they actually share a surface. The intersection is one, like if you have 3 three-dimensional bodies, their intersection is a 2-dimensional plane. We're not interested in the volume where they overlap. We're only interested in the horizon that they share. But the volume would also be interesting, but that's for another time. We're not going to go there now. So for now, just think about the 2 intersection points. Now, we haven't introduced any measures, but simply from the proportions and the relationships, if we start out with some geometric constructions, I'm sure you've all had this in the school that you would, for example, to find a center of a circle,
you pick a random point, you pick a compass, and then you make two equal markings, and then you pick either markings, and you make a cross up here and a cross up here, and you take the other one and up here and up here, and then you create the line, and then from that line you do it again somewhere else. You create another line. Okay, that's a very terrible drawing, but that's actually quite awful. But if you do this nicely, if you do this precisely, this construction, then you end up, if you do it right, if you do it precisely, not the way I did, you end up with the center. And you do this for the other circle. And so you can construct from the boundary, you can construct where the center would be. I'm going to use some other colors here to make this a bit more, let's see, intelligible. So now we can draw a line through these 2 points. And now you can start to see, if you have the radius, which, since we constructed the center of the circle, the radius is supposed to be equal all around. And so that means here you have the radius. I'm going to call this RL for large, and then here you have the radius. I'm going to make this in another color, maybe red. No, extra. The small circle, R small. And the same is of course true on the opposite side, right? Because you have a mirror symmetry here. And now, through these two intersection points, if we know that the radius ends at where the circle ends, but the line, of course, that leads to this intersection continues. So now you have a geometric relationship where this angle here, and I call this alpha and call this beta, then you have, through trigonometric rules, this is assuming for now Euclidean flat space and all the axioms that hold for parallels and all that. So we're starting out with standard Euclidean space. Then you end up with a trigonometric function. So we have gamma up here, and we know alpha plus beta and gamma 180 degrees. And so now, because the proportions, they're inversely proportional to each other, like the sides are scrap that. They're not. We don't need to go to the inverses here. Just the proportions of the sides are always related. Like if you think, for example, if you double beta, for example, if you would make beta something like, what is this? Yeah, it's almost here. It's roughly here. Then you would, by doubling beta, you would also extend the length of this line, the radius of S. Then you would have, like, for beta to be this large, right? To be symmetric, then the corresponding circle on the other side would have to be much bigger. Okay, this is getting a little bit confusing. I'm going to remove the circles and just draw the triangles. So we had the small circle. We have the larger circle. And then we have the triangle in between. You can still imagine, right, that you have this that these are centers, and that these, you would kind of think that there's the circles going like this. And now if you would increase this angle here, what we call beta, and you go to beta, whatever that thing is, then you would naturally also extend the length of R, and then now you would have to have the intersection point up here, right? That's how we got to the size of beta. And that means if beta increases, then the intersection point moves, and that means for that to be possible, that previously small circle now has to be rescaled to meet that And you see from what happened, from just imagining things and interprojecting it with each other, we suddenly discovered these sort of relationships. And these are relationships of proportions. At no point did it matter how large any of there's no inches, there's no meters, there's no feet. It's just angles and straight lines and circles around points. So these are purely geometric functions that have not introduced scale yet, but they already have introduced ratios of the two arms, the two radii, that we can derive from the position, from the angles where, like how large the section is, the measure between the two intersection points. Again, I'm only drawing one here, but you know that there was the complement, like this is still a mirror symmetry, and if I would have drawn it nicely, then there would be an intersection point down here where these two radii would meet, right? So you can see if you squeeze them more together, they would wander, but what really matters, what really defines this, is the proportion between the two spheres. And that piece, that proportion from one length, whatever the length is, a translation to another length is actually a piece of information. So now we generate it through a self-interaction, through projecting a purely imaginary thing into an empty canvas, into something that, like, something we imagined there to be space, and we imagined in that expansion that we could scope it, that we could have a bounded a limit, and then interprojecting it with another. And now through this self-interaction, we created a relation. And the relation is between the two circles, which could also be said is between the two intersection points, because that's really what is relevant in this picture. That the information is the pattern of these two intersection points, and you can track that pattern, right? If you rescale the whole thing, you can see that the intersection point maybe wander around. I mean, it wanders around both spheres simultaneously, right? I can draw a few examples, right? We can say it can be like this, it can be like this, two small ones. It can be like a large one and only barely intersecting. Still, I mean, technically, I still want to be actually intersecting, not just meeting. That means they're not meeting at one point, but they're at least crossing each other a little bit. That you have two intersection points here, two intersection points here, two intersection points here, or yeah, then also like the more obvious ones, where it's clear that you have, again, all of these are supposed to be circles. And so as you zoom the different circles and make them larger and smaller and move them around, these intersection points move around, but you can always see there's always one, and then there's the other one. And this is the story how you you generate duality from non-duality. In the tradition, Advaita Vedanta usually ends up with postulating the gross matter, the physical material realm, and the subtle matter. It's more subtle than just informational. We could say informational is more subtle than the physical, because the physical is gross and tangible, and then the information about the physical is a kind of like a second order, a type of meta information. And you can say you have the object is the car, and then the car is moving, so you could say that is information about the car, about the object, how it is moving within the larger context. So this sort of distinction is not an absolute one, but it rather describes two poles of a spectrum, much like if you consider the moon. I always like to imagine, we always look at the moon from the Earth, but I think it's actually much more interesting to look at the universe from the perspective of the moon, because, as you might know, we have the blue planet, and from the moon the face which is facing towards the Earth, that is always the same. So as if that face would be marked with a flag, let's say, and the moon would move over, the flag would always be pointing in the same direction. It would always be pointing towards the Earth, regardless of where the moon is. And that means from the moon's orientation with regards to the Earth does not change, which means if you would be standing here on the moon and look at the Earth, and you would observe the Earth rotate, as she does day by day, but you would basically look up into into your zenith, if that's directly in the center of the face of the moon, and then the Earth would, at a distance, would be hovering in space and rotate above you, and then from that perspective, then you would have the sun. This is obviously not proportional because the sun would have to be way, way, way further out. I don't have enough space. So the sun would then basically be going around in whatever it is, 28 point something days, a moon cycle, right? From the perspective of the moon, the sun is just like we perceive the sun to go around the Earth, which is not correct, because geometrically it's the sun which is pretty much in place, and the Earth is orbiting the sun, mainly due to its masses. But still, since we move with the body of the Earth, to us it looks like the sun is moving around. And the same is true on the moon. Like while the Earth is spinning on top of us, we would perceive and observe the sun to go around us, and therefore if the sun is on the far side, if the sun is back here, then it's only illuminated on that side, and then we have a new moon. And if the sun is directly above and it illuminates from the front, then we see everything illuminated, and it's a full moon. Good. So now if we look at this transition from, I'm just drawing this schematically, right? A new moon is the empty one, and the full moon is when it's well, maybe black is not the best choice. Huh? Anyway, it's one extreme of the position, and this is the other extreme, and then you have like the transitions in between, where you have a partial filling, and then you have a partial emptying. So, well, depending on how you look at it, like this is what the moon looks like while it's growing, and this is what it looks like when it's receding. In German, we have this trick that we can this kind of looks like an A if you start out, and this looks like a Z, like a traditional written Z. So we call this Z for increasing, zunehmen, and this is the A for receding or abnehmen. Okay. The main point here is that this is not a binary system with two states, full moon and new moon, but we have a whole continuum of different versions that continuously transform from one into the other over roughly 14 days, and then again on the way back. And this continuity in transformation, of transforming one into the other, is absolutely essential if we want to deal with things where we don't have a fixed raster or we don't have a fixed scale. The same could be said about waves. If we're dealing with waves, the wave equations, the mathematical principles, do not change what the liquid is made of or how much it is, or in an idealized case, right? So obviously honey is much thicker, and so it flows much slower, and water is more I don't know if ephemeral is the right word, but it's more probably a proper technical word for it, but it's more mobile, agile. How do I say this? It's this one. And so, but the waves, how they propagate, for example, in oil, which is thicker as opposed to in water, the mathematics are the same, and it's based on having a horizon, and then having displacement from the horizon. So for example, if you push the horizon down here, then you're displacing some water, and then you have, you necessarily generate something like this. And then because of the pressure, right, you have gravitational pressure here pushing up the displaced water back, pulling back down towards the ground. And then here you have the displaced forces that will eventually pull the horizon, like this surface, back into center. And so you could say maybe the next version looks a little bit where the displacement is a little bit less below the horizon, and the displacement, the peak is also a little bit less, but it has also expanded out further, and then the horizon coming now up goes first to center, and then it goes a little bit above, and then it goes a little bit more above, and then you end up with the opposite. And then, right, you have like, if you displace something, then you see that the water goes away, and then it comes back, and it goes away, and come back, and goes away, back. And it kind of oscillates until all the energy is dissipated, and eventually you go towards ever closer to equilibrium, until you return back to the original surface. So what matters is the displacement and the surface tension. Well, it's the core of all this can be described geometrically, completely invariant of scale. Only when you want to deal with a specific wave on a specific medium, on a specific planet, for example, where you know the gravitational attraction of the planetary body, and the mass of the medium, and its viscosity, and well, no, not the viscosity, like the specific weight would be important. Yeah. Anyway, so now we're with waves, with relative descriptions. What else did I want to go with this? Well, the fact that you have to describe a wave always with there being a peak and a trough, that you cannot have one without the other, that you cannot have a wave where the ocean is flat and then you have a wave like a hill. That doesn't work, because the water flows away and it goes back to equilibrium, and the energy will actually run off, and before you know it, you're back to a more flat horizon. And whenever you describe something by differentiation, you have to differentiate from a common reference point. Here we have the horizon of the ocean. In other cases, you could take the well, for example, you can take electric charges. That's what Dirac used with the Dirac-Z, that you have positive charges, positrons, and negative charges, electrons, and that you can excite them, and they create matter-antimatter pair, because like a positron is a negatively charged electron, essentially traveling backwards in time. And well, you know, this comes from CPT, like charge parity and time consistency, that you can have the same universe as this one if you change all the matter with antimatter, and then you invert. That's flipping the charges, and you invert parity, which is kind of well, you would have to look into what helicity is, like it's kind of like an internal orientation. So if you change the left-handedness to right-handedness, matter to antimatter, meaning charges, like electric charges, to their inverse, and you reverse the flow of time, then you end up with the exact same physical laws. So you could have like the antimatter universe versus inverted running backwards in time would just look like our universe running forward. And yeah, but since we did all this without introducing scale, we have we satisfy the criteria of scale invariance. And scale invariance is what can become very, very powerful when we have to deal with singularities. Because if you think of a triangle, if that's all there exists, this is the argument of Julian Barbour, then that triangle is entirely fixed by two of its angles in shape, and as long as these two angles are the same, then it doesn't matter what size the triangle is, because the size of the triangle is an intrinsic property, and the angles are, well, the size is an extrinsic property, and the angles are an intrinsic property. And the beauty in this is check. Okay. And the beauty of this is, even if you push I'm going to extend the lines here. You will see why in a moment. So if you here you could say, okay, if you move these lines further apart, then the proportions and the shape of the triangle is preserved, but its scale is changed. So this is zooming out, like translating all the lines in parallel far from each other, right? It's like, would be like a translation like this, where you go out like this, translation like this, where you go out like this. And then you have roughly the larger triangle, which I drew underneath. I hope you can see the congruence there. But if I go the opposite direction, then I can also move inwards. And I can move so far inwards, not only to draw ever smaller triangles, but if I keep going smaller and smaller, eventually they become so small that they can be singular points. But if I wanted to do this by a translation, let's say I take that line and I move it towards the center. And then I take the other line and also move it towards the center. And then I take the third line and also moving towards the center. Now we have a singular point where basically the distances breaks down, because in a point you can no longer have a distance. Even if you had a distance out here, it certainly can't hold in a point. However, the angle that we had on this angle is still preserved in this angle, and actually over here as well. And the same is true for this angle, because this angle appears up here and is inverse over here, and so on. This angle is preserved because you're only doing translations and shifting things around. You're not actually changing any of the angles. And that means by having simply these lines meet at this singularity, you can still reconstruct the whole shape on the other side. So that's a kind of an ability to project from an expanded structure through a singular point to its inverse on its opposite side. Right? And you would naturally, if you would do this, you would create the mirror image. So it's not the exact image, but the mirror reflected image, and it's actually reflected. This gave me quite some trouble when I heard Feynman pose these questions. Like, when you look at the mirror, why is left and right inverted but not up and down? And when you look at it like that, it can be very, very confusing. How does the mirror know that there's left or right a difference, and up down it isn't? And you can get quite lost if you try to answer this question in the wrong way. The resolution ultimately, you can pause here if you want to think about this for a moment. But the resolution ultimately is that, in fact, it's not left and right which is being flipped, but it is back and front which is being flipped. Because if you have a mirror, maybe I can go back to the camera. You can see my hacky. Well, not sure if I want to do that. But see how terrible this looks. Yeah, it's all right. Yeah, so if you have a mirror in front of your nose, it's not that the image is flipped point symmetrically, but it's actually like your mask is kind of flipped like this. Like the nose, which is the closest to the mirror, is then the first that you can see, and then if you go further back, that you have this, you know, like if you think of a glove, for example, that you can take off and you can flip it into the other way. That's the kind of reflection that we're observing with a mirror. But the mirror, of course, only as a surface reflects in one direction. So you can have a surface being flipped. Now we're talking about the same thing in 3 dimensions and actually plus time. And it flips only the direction of time, but not the content of time. So just like the geometric relationship that we have in space, as that is preserved, if you just translate the angles of a triangle through a point, you go to the other side, and then you have the same shape appear again. This is just like a simplified version of what we're talking about in more than 2 dimensions. And yes, this then takes us to scale invariance, and as you saw, like with this interprojection of the 2 circles where we construct the 2 intersection points, that gives us well, the interaction events, whenever things intersect, that is always local. I can't intersect or touch something somewhere where I'm not. It always implies that there needs to be locality, and that again is a very, very deep concept in physics. That the fact that we can interact is based on that we have a local access, a reference system, in the sense of like a root, where we, if you think of in Linux, for example, or Unix, you have the file system root, like just these slash and backslash. Well, use the one from the internet with HTTP. Don't use the one from Windows, right? It's the other one. So there you just say like, well, that's just a starting point, but it's recognized that a root is as good as any root, because root just denotes a sort of origin. It doesn't mean root in an absolute sense. Like if you have a laptop, you have a local root file system, but somebody else has another laptop and they have their own root file system. But you could map both file systems and then sharing the root. Find a better solution. Sorry for all the noise. This will hold for the next few minutes. And yes, so we can construct the interaction events which are local, and then from that locality, then we can have an origin, like the first interaction event, and then a sequence, and then that interval can be embedded in larger interval, or the different interactions which are local could be related to other interactions. And then from there you can build up a topological graph where the things are, in a sense, imagine that all the interaction points are elastic. Really not doing the best job. Try to be quick, but it's probably not the wisest. Trying to. Better fix 10 times than do it right once, right? Okay. So because we didn't start out with scale, we have a much more elastic structure now, and that structure is much more flexible, especially in a geometry which is not Euclidean. Even though we started out with Euclidean projection, that was just as an idealized case to generate the intersection points as a story, so to say, as a deductive device. What we really want are any sort of interaction points, and we don't actually care too much about how we got there. However, one implication in this, which may not be obvious, is since you have these relative proportions, you can apply this to anything, including frequency. And when you apply it to a frequency, like in a frequency, you say, like you have a sine wave, and then you have a period, which is like one full cycle of the sine wave. And if we use, okay, we have some background noise here, sorry, it's going to be over in a second. So if you calculate in radiant, then you always say 1 full phase is 2 pi in radians. But now if you change the frequency, you essentially change what you map pi to. We're very used to do this in signal processing, but if you wanted to derive what it means geometrically, you would ask the question not, okay, if I want to make a circle, I take the diameter and multiply it by pi. Right? That's my relationship from how how much curved a circle is, or how much larger the circumference is compared to the diameter, or how much smaller the circumference of a circle is than the square, right? That would be 4 times diameter, and then it's slightly less, it's 3.14 and so on. So that's how we usually look at it, because we take the numerical value of pi, and then because we're used to that, because we're used to use a reference and rely on a reference system of scale, that's what we tend to start out with. But that's not, I think that is unjustified. And it's, again, one of these intuitions simply because we have fingers and we can count on fingers, and then we learned about ratios and trading and calculating things, and we wanted to operate in a common domain. We constructed that domain, but then suddenly, because everyone constructed a shared domain or agreed to that shared domain, suddenly we kind of subordinated ourselves and started to assume that the external measure is primary. But there is no such thing as an external measure. That's not, it's not helpful to have a universal measure of space. Like, for example, the distance of a meter is defined by a certain number of oscillation of a cesium, whatever number atom it is, because we know precisely how fast that oscillates per second, and we know how much light travels within a second, and then we say, like, okay, so and so many of these oscillations which emerge because the electrons are moving around at the speed of light, and they're doing some kind of unbalanced interaction that lead to a high level oscillation, and that's then the clock that we use to count or to measure the speed of light for a given time, and then we say that's a meter. But that's a completely circular definition, right? If you would be in a spaceship and would accelerate and brake and go close to the speed of light and get Lorentz contraction and squash and stretch around, within your frame, subjectively, it would always be a circular definition, and you would always perceive a meter to be a meter and a meter, even though from the outside you may look really squashed or really dilated. So I'm just saying this because while we can export any given measure and we can adopt it in multiple contexts, for operational purposes, this is perfectly fine. But to start out with this on the most basic level is extremely problematic, because if you share the measuring stick, like the measuring rod, that means you share the same space. That means you are in the same frame. And frame of reference doesn't just mean frame of reference for time, but because this complex conjugation that you always have the real part and the imaginary part. This is just how we're doing it in math, that we assume as a reference the real line, and then we can Wick rotate into the complex plane, and that then tells us how much we're out of phase Wick rotated, and then that's a way to understand the distance of a Lorentz interval, like to the extent that something is rotated into the complex plane, that you have an imaginary component over the real component. The more you go into the imaginary component, the further you're away. And if you push this all the way to the limit, in the case of pi, right, pi would be half circle, and pi half would be 90 degrees. So if you start with the real line and you rotate by 90 degree or almost 90 degree, that here you have only real part and no imaginary part, and here you only have imaginary part, no real part. This is true as a mathematical statement, but as we've just seen, this is also true as a conceptual statement, because we actually use the concept of imagination, of projecting something, essentially generating or making up something informational about the physical without affecting the physical, but still based on the physical, and therefore enriching or extending the physical. And you can always translate one into the other. Again, this is Wick rotations and Lorentz contractions are the kind of topics that you want to study if you want to explore this further. And we can also do this together if there's interest. We can explore these sort of structures. What are the implications? How do they behave? And one of the aspects of this relationship between space and time is, if you force everyone into the same spatial frame of reference, you also implicitly force them into the same temporal frame of reference. And that is approximately true on kind of high level
coordinations, like, you know, when to get on a flight, and then when the flight is going to arrive on another continent, or if you want to synchronize, okay, it's your 10 o'clock, it's my 4 p.m. or something like that. On that level, it is approximately true. But when we go towards high frequency trading, where we have the additional challenge of these like options, this is now just a little bracket that we can explore later. Black-Scholes, these are partial differential explosions, which kind of underpin the options pricing on the stock market options. And because they're partial differential equations, they are mainly controlled in the derivatives, which means the price of an option is primarily dependent on the volatility, like how unstable, how volatile, how like unstable in the sense of not still, but how much its price changes. That determines the price of the option, and the offset of what the actual price of the underlying share is basically irrelevant. And this already may sound like, if you're not coming from finance, this sounds quite absurd, right? How would an option be disconnected from the actual thing that you're trading on? But in finance, this is actually the default scenario. And I'm saying this is because we're using mathematical devices and infrastructure that are not cut out for the stuff that we're using it. If you're just trying to have futures options because you wanted to, I don't know, create a sort of kind of a hedge or insurance of price stability for wheat or for corn over stronger and lesser seasons, you know, I can understand how we got here and how we built something like this. But now that we deal with high frequency trading where the volatility is much higher because the trading frequency is so high, then the time sensitive component becomes dominant, and the metric component, like that one where we associate the scale, in this case price, that becomes completely irrelevant. And now we're operating infrastructure on the very edge where it's breaking down. Not where it holds, but the furthest away from this that we can go. And then it becomes this complete, in my opinion, nonsense of pure speculation that we're just maximizing variety, in a sense that the best thing that you can possibly do is bet on something where you think you can bet better than everyone else is betting. But it's just like, you know, betting on horses. Everyone is betting, and your guess is kind of excluding insider trading, which would actually be a part of information, but then you introduce other problems based on how our market's set up and how so that's not really a path that is an option. But at the same time, the infrastructure that we're operating, where we have a measure of let's say a transaction, even if you pick $1, €1, whatever, and you make a transfer. Usually we use a timestamp and say like, okay, the transaction happened then. But if any amount would be transferred as an instantaneous action, then you would you break calculus, right? Because calculus says like the change over time, right? I accelerate with a certain force, and then that force accelerates my car over a few seconds, and then over the few seconds the velocity gradually increases. But if I say the velocity is flat or is static at whatever speed, and then it jumps, like I increase it by 1 in a moment, then the derivative of that, the force that I would have to exercise, because it's no longer not just over a short period of time, but over a serial period of time. In a moment I change the velocity, that means the force would have to be infinite. The same way would be for monetary change. If you transfer any amount, even if it's a cent, even if it's just the smallest weakest unit that you can think of, if it's instantaneous, the rate of change would still be approximately infinite, because you would divide the change over duration, which is approximately 0. And these are just like all sorts of problems, the way we use numbers, the way we do accounting, the way we store data, and then what we try to extrapolate, right? Then we look at many transactions, and from many transactions we try to reconstruct the temporal information about the rate of change, which you know, given what we operate today, it's kind of like the best in the sense of like the most useful thing to do, but that you have to reconstruct and rederive the information which you lost. But since we are primarily sensitive to the temporal component, meaning the change over time, it seems silly to operate an infrastructure which is unable to cope with duration, and where we do the accounting of changes at moments in time. And this, again, this is an idealization where in some cases you're perfectly allowed and welcome to do some idealization, but this is not one of those cases. This is one of the cases where if we pretend that transactions happen at a moment in time, we cannot deal with derivatives, we cannot do calculus, and all the infrastructures that we build on top is basically just patchworks. It's just like fixing the mistake of dumping or not recording the information which was relevant, and then trying to reconstruct it later. And so you see this approach to scale invariance, to projective and transformational continuity, and this ability to be robust by transitions where we cross singularity. Either that's the beginning of the universe, or it's some other event horizon, or it's a moment in time, or it's an informational boundary. Whenever we need to be able to correlate across a boundary, we need to be able to have to identify localized points. In the previous example, that was intersections, to identify a pattern, and then however the lines move, you just trace the intersection. And while they intersect with each other, the pattern can always be localized. And yeah, just as a closing remark, because that's another subject I want to go into in its own time, is what I earlier said. If you could perceive everything that you perceive, including the history associated with it, so that means the previous states, but also the previous interaction history, that's actually suggested by Edgar Mitchell. So Ed Mitchell was an Apollo astronaut. He was the 6th man on the moon, and had all sorts of interesting side projects that we might have a chance to go. Well, I'm not gonna tease people. So this is something that I learned through a talk. I think Annie Jacobsen was on Joe Rogan or something like that, and she talks about, she's a journalist, and she brought some information to the public from mainly retired government sources in the US. And among one of the people that she spoke to, well, she stumbled upon a picture about Ed Mitchell on the moon having a map. And it's like, okay, I mean, what leads to a situation? I mean, first off, if you're out in space, and you have to take all sorts of consideration. It's not that you find something randomly in your pocket and you pull it out, right? You need to have the steps that led up to just the construction of a map for the moon that is relevant to where they are, right? Because they came in a capsule and they were supposed to land something, and they were supposed to land something very specifically, because they had a parallel mission that was, I mean, it was official, but not many people knew about it. And apparently they got lost today, in a sense that they got displaced. And anyway, so yeah, there's a lot of interesting kind of tangents going around that. And yeah, so basically, what I'm saying, Ed Mitchell, that's not just some random kid. This was a guy who was highly trained professional, was a fighter pilot, test pilot, then went into the Apollo program, had a PhD, I believe, in astrophysics. And, I mean, trained throughout his life for all sorts of extreme circumstances, which required responses and actions that were highly coordinated and had to be precise and exact and reliable, and otherwise you can't fly around in space with just kind of haphazardly trying what you're doing, right? And on his way back, he was mainly responsible for the lunar module, and so once they came back from the surface of the moon and were back on the way back to Earth, they were what he calls they were in barbecue mode, where the craft was rotating
in a way so that the sunlight would hit it from different angles, so it wouldn't get overheat on one side and freeze on the other side. So they called it barbecue mode. And so him having a little bit of downtime was looking at the out into space and seeing the moon that they just left, pass in the rotation, and then the Earth at the horizon, still being fairly small. So if you're standing on the moon and look at the Earth is roughly twice the size from your relative perception. Like it appears twice as the size in diameter than the moon does when we look at the sky from here. Just so you have some proportion. The sun, of course, looks the same because it's so far away. It doesn't make a difference whether you're on the moon or the Earth, the relative size. So in that process of just seeing like the moon and the sun and the Earth kind of pass by again and again and again, he dropped perhaps in almost a bit of a trance-like condition where he was relaxed, he was aware. Like, imagine you must be very excited and awake from having just explored something very far out on the edges of what our species has explored so far, and then you relax into a calm, clear state. And in that state, from his training in astronomy, he reflected and thought about, how magnificent is it that we physical beings from one body in the universe are able to not only move, but if you think about the history where all this came from, because from our understanding, again, the sun only fuses hydrogen into helium. So anything heavier than helium in our solar system does not come from the sun, because the sun is not set up to generate carbon, iron, and these heavier elements. They come from supernova explosions, and they are fused in heavier stars that exploded a long time ago and provided the matter for the solar system that we are today. So if you pick any two carbon atoms, chances are that they actually originate from different explosions of older stars. It's not that all the matter we have, that there was a star that exploded and now we have all this new stuff. It's like, no, there were all sorts of stars going off like fireworks all over the cosmological scales over billions of years, eventually forming the nebula, which eventually provided the nursery for our galaxy and then within the galaxy for our solar system to form. And in that recognition of this sense of deep unification, recognizing that the different atoms being kind of, Carl Sagan used to say, we are star stuff, stardust, star stuff. That the matter that we're made out of comes from a very long history, and now we have this differentiated structure, and where we have this very hostile environment like empty spaces, we're not very adapted to go out into space, as opposed to tardigrades, for example, which apparently you can suspend to absolute zero and they just kind of arrest and they kind of are frozen into place, and you can leave them as long as you want, even for years. And then when you heat them back up and they are they get in a sense they melt, they start living again, but they're considered to be animals, and they're actually in every raindrop. I don't know, there's like thousands of them. They're like tiny little they're not bacteria, but if you think of a bacteria as a small living thing that can be in somewhere, that's roughly how you can think of a tardigrade. They sometimes they're called water bears. So like very fascinating creatures, have like these 8 kind of trunk-like legs. And but again, to me, the thing that's most fascinating is that they can suspend, essentially hibernate in empty space at absolute zeros and withstand some pretty extreme conditions. Anyway, Ed Mitchell was not talking about tardigrades, but what he was talking about was this whole history of trying to understand what was going on, how we end up with a consistent reality where we can interact and communicate with each other, understanding the mathematics behind quantum mechanics and understanding the cosmological history or story of how the universe formed. He entered into a deep state of an ecstatic bliss that none of his partners around and fellows in academia or science or even philosophers could give him any understanding of what that could possibly be, until one of his
acquaintances. I'm not sure how the relationship was. He was familiar with some Eastern traditions and said, like, look, what you're describing is this state of non-dual experience to experience on a very, very deep level, this total sense of unification. That sounds like a samadhi experience that meditators and yogis will talk about. And then, so from there, then he started, he opened a dialogue with Gopi Krishna and wrote him letters, letters which I actually held in my hand. Like I went to the library where the estate of Gopi Krishna was preserved, and therein was the letter, and it was quite an adventure to kind of see what him coming from this highly Western trained, specific military scientific background talks to a Eastern mystic. And Gopi Krishna often is qualified that, you know, that some of the statements he makes are incorrect or imprecise. And okay, that is true. I would not say to read Gopi Krishna and just kind of assume that he's always right. But at the same time, when you read his stuff, you can see that he wasn't properly trained. He wasn't properly educated in the things that he talks about. Because if somebody tells you, gives you a reference understanding, some more noise. They're boats, and I like boats, so it's not a big issue for me. But I guess acoustically, maybe disturbing. So having this if somebody gives you a conceptual framework to think and reason, then it can be very tempting to it can be very tempting to adopt that belief system, whether it's warranted or not, and so we can carry biases forward. So lacking that kind of precision, or precision in the sense of like a precisely defined structure, and just kind of talking about experiences may be a little bit clumsy. But if we accept that sometimes when we're just fishing for words that we don't necessarily capture the right expression, then we can get some leeway at the on the upside. We might get some very genuine insights that you can really tell that somebody is trying to capture an experience and trying to convey it, even if it's maybe not in most precise terms, maybe sometimes not even technically accurate. But if you can relate to the experience, it can be extremely valuable, because you can be sure that is not somebody just reciting some scripture that they picked up. Because if they did that, then they would actually say the same thing that the scriptures would say, or you know, some Buddhist practitioner meditation manual or whatever resource where you have such experiences referred to. So again, that to me was very, very interesting, and I just wanted to introduce the character briefly. Mainly Ed Mitchell, because after he came back as an astronaut, he worked on he published a paper called Nature's Mind, the quantum hologram, where he describes how a physical body could be not only a reference in the sense of like an access point that gives you access to your memory, but how a molecular, a composite structure could, in a holographic sense, provide not only the access key to the information, but actually encode all the information upon that physical representation, so that in a sense that each object carries with it its own history, its own reference, all the way back to wherever it originated from. We have it's not just that we don't have the tools to explore the origin of, for example, the matter. Like, this is the question of leptogenesis. It's not just that we can't conclusively, definitively know that, but we don't really have models that allow us to go there. And I want to stress this point again. Whenever we hit singularities, whether it is in a black body radiation, when you have like the core of the nucleus, or whether you have Schwarzschild horizons in the case of a black hole, or if you have an extreme condition like the early expansion of the universe, in all these cases, all we know is that our concept of space and time, the way we operate and the way we structure reality on the basis of human cognition, this spatial 3-dimension and time, this breaks down, and that those models are no longer valid. They're no longer useful if we're going beyond that. But that doesn't mean that they're not accessible. But if we want to access this, I think it's very unlikely that we just will randomly hit the lottery and guess the right thing, even though it's not a bad idea to guess what it could be. But we still want to use our intuitions and kind of and sometimes maybe oppose our intuition. If our intuition says one thing, let's see what happens when we consider the opposite. Always also consider the alternatives and try to gain more and more insights. What I'm about to say about Ed Mitchell is not addressing leptogenesis, but after leptogenesis, once you have particles, basically all the interactions would be inscribed of sorts in all the matter. So the carbon atom in my hand, for example, if I would pick one, if I would know how to access it properly, you could probe its history, and through its history decode its previous interactions and possibly identify that some came from the same source or share an interaction history where others are distinct. But that, again, that requires a model, and that requires a setup that allows you to probe for specific to check whether an interaction was the same or it was different. In the lab, we got pretty good at this. We were able, I mean, not me, but like us as a species, we got to the point where we are able to decode through entanglement, not just the correlations, but also to probe entangled histories. Frank Wilczek has a speech on this. I think it was his introductory lecture that he gave kind of as a welcome when he migrated or became a fellow. I'm not sure if he relocated, but he joined Sweden after having already won the Nobel Prize. And in his introductory lecture, he talks about entangled histories. It's on YouTube. And there you get a sense of how far this can go to extract temporal information, which is not looking at physical corrosions or imprints and then as an artifact kind of imagine and project a story, but this is now these are now physical experiments that allow us to take a particle and probe whether it had one history where it took a particular path or had a particular interaction or another. So these are not purely speculative ideas, but they are quite tangible. But underneath all of this, I think much more than anything else is this principle of holography, and that we have data structures which are consistent with holography, which means they need to always resolve to a systemic view from local information, and local information always can only make use of a scale locally in a local frame, and from local frames you can construct a shared frame. But there is no absolute frame, and there's not like an ultimate frame, an ultimate background which provides a measure. That's just the conceptual space within which you can meet and interact with other parts which locally can advocate their own scales, and then you can have a ratio, a relation to rescale these notions of distance and duration. And yeah, so the quantum hologram, where the important about a holographic system is in any recursive system, the one operation you always get for free is the merge operation. So if you have a recursive system and you have this and that, then you have always the composite of the two combined together implicitly available. Not that you need to combine them together, but you can always just refer to them as the composite or into one of its parts. And the same is true for the quantum hologram, that if you have, like the chair that I'm sitting on has its own history where all the different parts came from. But if I would just shave away a bunch of parts and just take one wheel of the chair, then I could still from there locally obtain the information that is encoded relating specifically to the wheel, and the wheel becomes the access object, the reference to its own history, while the composite of the chair as a whole becomes the composite reference to all the different parts, as well as its shared and interrelated history. Okay, so that's it for now, and you're welcome to let me know if something particularly spikes your interest, or if you would like me to explore in one direction or another. So I'm very happy to be responsive and shape the course of this exploration and discussions in a way which is most I don't know, interesting or useful to others like yourself. So I hope that was interesting, and we'll keep going into specialized aspects of this in future sessions.